Water has been found by the James Webb Space Telescope on a mysterious planet. Precision instrumentation and Webb's giant mirror work together to record the most detailed spectrum of an exoplanet atmosphere ever. Exoplanet enthusiasts have experienced a spectacular dream come true, as NASA's James Webb Space Telescope has proven its unparalleled ability to study the atmosphere of an exoplanet more than 1,000 light-years away, with the use of its 270 square foot or 25 square meter mirror, precise spectrographs, and sensitive detectors. Webb has, in a single observation, found evidence for clouds that were previously believed to be missing, the unmistakable signature of water and hazy hints. A small preview of Webb's exciting future of exoplanet exploration may be seen in the transmission spectrum of the hot gas giant WASP 96b, which was obtained using the near-infrared imager and slitless spectrograph, also known as NIRIS, on the telescope. The hot, puffy gas giant planet that orbits a far-off, sun-like star has a clear signal of water in its atmosphere that NASA's James Webb Space Telescope has observed. Scientists had previously questioned whether the planet could support life, but NASA revealed on Tuesday that JWST had found indications of haze and clouds, as well as the distinct chemical signature of water vapor in the planet's atmosphere. The planet's surface is around 1,000 degrees Fahrenheit because it orbits its star so closely, at just 1/9 the distance between Mercury and the Sun. It is not a likely contender for alien life. But during the upcoming years, scientists hope to improve JWST's observations so that it can look into the atmospheres of smaller planets that orbit their stars at a greater distance. This is only the start. We'll begin descending to farther, smaller worlds. Scientists working on exoplanets remarked during a NASA live broadcast announcing the new discoveries. JWST is anticipated to capture direct photographs of planets orbiting other stars in the upcoming years. JWST, which was put into orbit in December and has already reached a distance of 1 million miles from Earth, is now completely functioning. On Tuesday, NASA revealed the telescope's first comprehensive data and full-color photographs. The visuals are astounding. It provides astronomers with a degree of clarity they could only have imagined until this week, revealing individual galaxies, exploding stars, and clouds of compressed gas giving birth to new stars. However, spectroscopy, the technique JWST utilized to find water vapor in the atmosphere of this far-off planet, will account for the majority of the mission's scientific findings. The telescope is equipped with tools that enable it to dissect infrared light from far-off objects and determine where it falls on the light spectrum. In essence, they disperse the light into an infrared rainbow. Since various elements reflect different wavelengths of light, scientists can identify the components that make up an item by analyzing the light spectra that it emits. The observation, which shows off Webb's amazing capacity to study atmospheres hundreds of light-years distant, is the most thorough of its sort to yet. Based on minute reductions in the brightness of various hues of light, it indicates the existence of particular gas molecules. The Hubble Space Telescope has studied the atmospheres of several exoplanets over the past 20 years, and in 2013, it made the first definitive discovery of water. However, Webb's quick and more thorough study represents a significant advancement in the effort to identify potentially hospitable worlds beyond Earth. The Milky Way contains WASP 96b and more than 5,000 other exoplanets that are known to exist. It is a particular class of gas giant that is 1,150 light-years away in the southern sky constellation Phoenix and does not have a direct analog in our solar system. With a diameter 1.2 times larger than Earth and a mass less than half that of Jupiter, WASP 96b is the puffiest planet in our solar system. Furthermore, as the temperature exceeds 1,000 degrees Fahrenheit, it becomes noticeably hotter. Every 312 Earth days, WASP 96b completes one full circuit around its sun-like star, orbiting it at a distance that is only 1/9 that of Mercury from the Sun. Due to its large size, fast orbital period, puffy atmosphere, and lack of light pollution from nearby astronomical objects. WASP-96b makes an excellent subject for atmospheric studies. On June 21, the planet was tracked by Webb's near-infrared imager and slitless spectrograph for 6.4 hours as it crossed the star. The end result is a light curve that shows how starlight is reduced overall during a transit, as well as a transmission spectrum that shows how different infrared light wavelengths between 0.6 and 2.8 microns vary in brightness. While the light curve confirms characteristics of the planet that had already been established from other observations, such as its existence, size, and water signature, the transmission spectrum reveals previously hidden details of the atmosphere, such as hints of haze and proof of clouds that were previously believed not to exist based on observations. And a transmission spectrum is produced by contrasting the unfiltered starlight seen when the planet is near to the star with the starlight that is filtered by a planet's atmosphere when it passes in front of the star. Based on the absorption pattern, or the locations and heights of peaks on the graph, scientists are able to identify and quantify the abundances of important gases in a planet's atmosphere. Atoms and molecules have different patterns of wavelengths that they absorb. Similar to how persons have distinguishable fingerprints and DNA sequences, the spectrum of WASP-96b obtained by NIRISS spans an astonishingly wide range of wavelengths, including visible red light and a region of the spectrum that has never before been accessible from other telescopes. It is also the most detailed near-infrared transmission spectrum of an exoplanet atmosphere ever recorded, meaning wavelengths are longer than 1.6 microns. Particularly sensitive to this region of the spectrum are water and other significant molecules like oxygen, methane, and carbon dioxide, which are not immediately visible in the WASP-96b spectra, but may be detectable in other exoplanets planned for study by Webb. The spectrum will allow scientists to quantify the amount of water vapor in the atmosphere, set limits on the abundance of different components like carbon and oxygen, and calculate the depth average temperature of the atmosphere. Then they can extrapolate from this data to draw conclusions about the planet's overall composition, as well as how, when, and where it originated. The best fit model is represented by the blue line on the graph, which accounts for the data, the known parameters of WASP-96b and its star, such as size, mass, and temperature, and assumed attributes of the atmosphere. How can a telescope examine the atmosphere of a planet? The procedure is actually quite easy. Light from the star must traverse the atmosphere of the planet when it moves in front of its star. As it does, the light will be absorbed by atoms and molecules in the atmosphere, who will then re-emit it into space. The photons that are absorbed by electrons in atoms' orbits will provide the electrons energy. The electrons will then jump to a higher energy level as a result. The electron will then release the identical photon and return to its initial energy level. Because each atom in the universe has a different energy level, it is interesting to note that by measuring the energy of photons, researchers may identify the atoms that absorbed and emitted those photons. As a result, it is possible to identify an object's composition by examining the light it produces and absorbs. The molecules in the atmosphere of a planet absorb and emit starlight as it travels through it. With the aid of a spectroscope, researchers can ascertain the makeup of an atmosphere by examining the light that travels through it. The measures are extremely clear and detailed because to Webb's innovative design, its gold-coated, 270-square-foot mirror is efficient in capturing infrared light. The light is split into hundreds of infrared color rainbows by its accurate spectrographs. Additionally, its highly sensitive infrared detectors detect the smallest variations in light. The difference between green and yellow is around 50 thousandths of a micron. And NIRISS is only able to distinguish brightness changes between those colors by a few hundred parts per million. Additionally, Webb's extraordinary stability and orbital placement near Lagrange Point 2, which is around 1 million miles from Earth's atmosphere, and its contaminating effects allow for an uninterrupted view and clean data that can be processed swiftly. Only a small portion of what Webb will be able to learn about exoplanets is revealed by the extraordinarily exact spectrum, which was produced by simultaneously analyzing 280 distinct spectra throughout the period of the observation. Over the course of the following year, the surfaces and atmospheres of a number of exoplanets, ranging in size from tiny rocky planets to giants rich in gas and ice, will be examined using spectroscopy. Nearly a quarter of Webb's Cycle 1 observation time is spent researching exoplanets and the elements that make them up. This nearest image illustrates Webb's capability to precisely characterize the atmospheres of exoplanets, including those of planets that may be habitable. Thanks for watching. If you enjoyed the video, subscribe to our channel and hit the like button. Until next time.